Okay, hello, everybody. Welcome to the April 2025 general monthly meeting of the Howard Astronomical League. We've got a pretty cool speaker tonight with all sorts of swag and gizmos, and so I think and we've got a regular program here, so it should be a pretty good meeting. So without further ado, our agenda tonight. We'll do some introductions, a few announcements, talk about the book of the month and our website. Then we have our speakered feature, our featured speaker. Mike Taylor is here, and he's with SSAI and NASA Goddard. And then we'll do our regular What's Up in the Sky, and then we'll go through some images. So if you're an introvert, don't feel obligated to, but if there's anybody who is online that's new that would like to introduce themselves, by all means, say hello, or if anybody in the room is new and would like to say hi. Okay. Oh, we have one person in the room. Hi, Molly. Welcome to Howard Astronomical League. Hopefully there'll be time at the end of the meeting and we can chat a little more and find out about your interests and how HAL is relevant, hopefully, to you. Okay, so anybody else online? All right, well, let's move on to announcements. So first off, we have our just to let everybody know, we've got our members only star party coming up next weekend, and Mike Krause will be hosting that. And then we have our next public star party on May 3rd with Joel, Chris Miskowitz and Chris Todd. Coincidentally, two former HAL presidents will be hosting the star party. And then recent events, we had this last month's public star party. It's kind of confusing to me because it's happening right at the beginning of the month. I think of it as the last month, which is March, but our April star party was held on 4/5. It was Jose, myself, and Richard hosting. I thought it was going to be a terrible, I thought it was going to be one of those cases where you show up and it's pouring rain and nobody's around. But as it turns out, it was pouring rain, but a lot of people came out. It actually wasn't pouring rain. It was just overcast. And then it started to rain at around 9 and we shut it down. But around starting from 7 or, near sunset till 9, we had about 40 different members of the public show up, and we, talked about the club, gave them a tour of the observatory. Here are two pictures of that night. Crystal Roland was there with, she's having an event tonight. She's at the telescope eyepiece right now, so she's not here. Crystal is our librarian. But she had a little activities table set up, and there were kids in the corner doing stuff, coloring rocket ships and doing other astronomically related activities. And even though it was cloudy, like you could sort of see the moon through the clouds. So the observatory was trained on the moon, and every once in a while they slewed over to Jupiter and Mars. They were very, very mucky because of these seeing conditions, but we had actually wound up having a pretty good time. It was surprising. I think it's a testament to how vital the club is right now. So that was good. Upcoming events this coming Saturday, that is in a couple of days, is the Earth Day at the Clarksville Commons event, where HAL will be there with their booth. Are you going to be there, Phil? Can't be there this time. But we have I think about 4 or 5 HAL members will be there. We'll have a booth set up, and the swag has been ordered. It hasn't arrived yet. We just ordered some new things to have at the table to show people. But there'll be people there with their solar scopes and representing. It's in Clarksville on that Commons out down that just off of 108. and it's usually it's a nice event. Lots of just general people coming by and introducing themselves and getting to know the club. So if you're free, feel free to stop by the HAL table. Other things going on is it's International Dark Sky Week this coming week, and you can learn more about what's going on and how to support dark skies if you go to the the International Dark Sky website, which there's a link on our webpage. And then we have a members star party coming up on the 24th with Mike Krause, as I mentioned. And then the other thing, which is in red down here, is it's still TBD exactly when and how, but we think we're going to have a star party. We're still trying to figure out what the best day is in terms of the light of the moon and the conditions and whether there will be enough people available, etc. But we want to have a star party that's dedicated to new members. So our members that have more experience in the club, we're going to recruit a bunch of them to be sort of mentors and not bring their equipment, but just be there as a resource for any new members who want to come out with their equipment and new gear and want to sort of get coached along on how to do it, be it visual or photographic or whatever you want to do. Though we're hoping to have somebody there. And as part of that, we want to have like new member month. So we're going to have a HAL meeting, and again, we haven't decided whether this will be. It might be May. It might be after that. I don't know. We'll see. But we want to have another club meeting like this with speakers that are dedicated to kind of the fundamentals of astronomy. We've already got one speaker lined up that's going to talk about the human eye and how the human eye responds to light and why you want to do certain things at the eyepiece and other things not at the eyepiece.
I'm sure we have a lot of pupils in that house.
Phil, we miss you here. Can you say that louder?
I said we have to make sure we have a lot of pupils out here.
If you didn't hear that, it was a pupils joke. Okay. Anyways, that's what's coming up. And the next thing, because so many people, myself included, worked so hard on creating our new website that I just can't stop talking about it. So I'm gonna let you know that. Oh, and also because Crystal can't be here, I thought I would highlight something. Let me click on this and see if it. Okay, it did come up, but it came up on my screen. So here's our website. There's our speaker for today. Look at that. So you may already know this. You may already have been here, but the website has this nice little wheel here that kind of goes through some of the recent events. This carousel, I guess it's called in web designer parlance. It also has this upcoming events window. If you click on this, you can get like a Google Maps link to the. I don't know what I just did. I clicked on something. If you click on this, you get back to the home page. So yeah, you can get Google directions and calendar stuff right to our meetings or the upcoming events. But what I was going to talk about was under resources, under HAL Library. So we don't have a book of the month this month, but if you're interested in looking for something to read, you can always go to the website, library, book of the month, and then it'll bring you to this shared online document that Crystal created, which has all of her books of the month. So if you're looking for something to read or for something that you want to recommend to somebody to read, there's all sorts of good things here. And her last month's book, this one, I checked it out from the library. I'm reading it right now. It's really good, actually. Yeah, it's good, isn't it? So kudos to Crystal for doing all this and for setting all that up. The other thing that might be worth mentioning is if you click on this HAL Library button, then a listing of all the books in our HAL Library comes up, and you can, it's not like a smart checkout or super, it's right now it's just a text listing of all the books in the library. But the web team is working on getting a library plugin, and making it more like easy to check out books online and stuff. So that's on our to-do. Yeah,
Is 100% of the inventory of the books online?
it is. What's
Okay.
not there is an up-to-date status on whether it's checked out or not. For that, you just have to email Crystal. I think there's a link to her personal email or her HAL librarian email address. So yeah, 100% of what we have is there, but the current status, like I don't think it knows. Maybe she did something, but I don't think it knows that I have checked out the last month's book of the month. Anyways, there's a lot of cool books there. People have donated a lot of really like legit solid astronomy books. Okay, so that's my little commercial. I'm gonna keep doing this, maybe focus on a different aspect of the website again, because I'm proud of the work that all these guys did to make it. And now our speaker just left to go to the bathroom, I think. He just walked out a second ago, so does anybody does anybody would anybody like to say anything? Any news or updates that are going on in the club, online or in the room?
You want to jump ahead and do one of the other items?
And he's back.
Yeah, there we go.
So it's perfect.
Of course you do.
Yeah. So our speaker is Mike Taylor, and he is an outreach scientist with NASA Goddard. He's been doing it for 17 years through his company SSAI, and he's got degrees from the University of Maryland, works on this climate change initiative as an education ambassador and a board member of the Clean Air Partners. All sounds like awesome things. And he's been working on something called Stella, which he's going to talk about today for the last 3 years. So without further ado, I would like to welcome Mike.
Thank you very much.
So do you want to just, are you logged on to the Zoom call?
I am.
So you want to just like share your
That's
screen?
what, yeah,
Okay, so I'll stop,
if you don't mind.
stop sharing.
Do I need to turn on the mic and all that sort of stuff?
No, you just, the mic is actually here.
Okay, you got it.
You want to plug in?
Yeah, I got one.
Oh, you got yours? Okay. Can I leave my machine here?
Can my machine sit on top of your machine?
Yeah.
Because I need the HDMI cord.
Oh, you do, you want the HDMI?
Yeah, yeah. If you don't mind.
You want to push this.
Yeah, I don't, that's kind of precarious. I was.
Hey, Victor, if anybody in the room is speaking, I think we lost audio.
I think you're on mute.
Sorry about that. Can you guys hear us now?
Yes, I can hear
Yes.
you now.
All right, sorry, we didn't set up ourselves properly. So I think you can still share your screen.
Yeah.
With the, so if you,
You have to go in those permissions, right?
yeah, I thought I did already.
Lost audio, it's back, I can hear it.
So,
I'll stop sharing and then reshare it.
okay, you should be able to share your screen.
Okay, I'm sharing it.
Now just drag it over to that other desktop though.
Which other different?
To that screen over there. Or share this screen.
I'm trying to share this screen right here.
Is anybody seeing, Mike's screen?
Yes.
Yes,
Okay, so you're sharing your desktop here. Can you tell your machine to display duplicate the display on both screens so we can see it in the audience?
Oh, okay. Wow. Wouldn't you have to do that through the Zoom call and have mine
He's
as
not tied into the,
mine as the main
he's
presenter?
not tied into the, through the HDMI.
Yeah. I need to be the presenter now, I guess, or something like that.
I'm
Yeah.
not entirely sure what,
Just put us up, just.
can you
That
drag
looks
that to
good.
that other screen?
Victor, just
No.
put the screen up that everybody else is seeing, just put the group up there, we should be able to see it.
That looks good online.
All right, here we
There you
go. Still look good online?
Yes.
Okay, we're good now.
All right, cool, excellent. Alrighty, so, as you saying, I mean, it happens. It wouldn't be something like this, if, there weren't a technical glitch. So I might be a little over caffeinated, a little under caffeinated, but, my name is Mike Taylor. Been, like you said, an outreach scientist at NASA for about 17 years. Okay, and in the past 3 years, I've been working on Stella. All right. Before that, and actually during right now, I'm still doing Landsat. So in order to understand Stella, you got to understand a little bit about Landsat and all that sort of stuff. So I'm going to tell you a little bit more about myself and how things developed and all that. So Landsat has been operating for over 50 years. Okay, from 1972 on, measuring the entire Earth's surface every 16 days per satellite. We have 2 up right now. That's Landsat 8 and Landsat 9. Okay, and that means every 8 days there's another complete observation of the Earth's surface with the Landsat series of satellites. Okay, and it's actually now going to be, I believe, 2031. Landsat next is due to go up, and so there's some more information about that back there if you're interested in that. Okay, I started work with NASA around 2008. Okay, on the outreach team. I got my my BS, my bachelor's in geography in 2009, and then my master's in 2013. All right. Go through that. So there's that timeline. All right. So, and then I'm talking about my journey through NASA here, and see these are some of the highlights here. So you can see me standing in front of the Landsat 8 rocket right down there in 2013. And it was incredible. One of the, just perfect launch, beautiful day. Everything was great. Landsat 9, there was a marine layer over there, and you saw maybe about half of a second before it just blipped right out of the sky, And so you got to hear it. But Odyssey of the Mind, one of my favorite outreach events ever. If you haven't heard of Odyssey of the Mind, basically it's for like middle school kids. They're at their peak nerdiness, and of course I'm a giant nerd, so it was just, it's amazing, and they ask some of the best questions, and they're so enthused. It's literally one of my favorite things ever. The Landsat 9 launched there with some of my outreach team. That was quite amazing. There's actually a whole geo tour out in Lompoc if you ever go out there, I would suggest going around there, near Vandenberg. Okay. 2024, you see Bill Nelson there, and I'm talking to some random folks over there, and then he comes up and smiling at me, and right in the middle of my talk, was like, "I know you're there, sir. I'll be with you in just a minute. Let me talk to finish the spiel and all that." And yeah, he was just amazing. And why am I showing just two little pictures up there at the top? Okay, those are images I created, and that's out of National Geographic. Okay, and of course, that's sort of like a bucket list sort of thing. I mean, even though they're small, I'll call it a win. You know what I mean? And then there's me and some of the team in Denver.
For anybody who doesn't know, you want to say who Bill Nelson is?
Oh yeah, he was the last NASA administrator. All right. And so we got the Earth Science to Action strategy. Okay, and so this is what we're trying to sort of do with our outreach and all that. And get across to folks, and have them start to understand what it is we do at NASA, and of course build upon that and build up the knowledge and so on and so forth. So what is remote sensing? Okay, so with Landsat and all that, and I'm going to go to the Landsat well quite often because that's where I derive my pretty much my whole outreach training from. We're looking at surface reflectance of the Earth for the most part. Okay. And seeing what goes on there. The Earth is very dynamic. It's changing all the time. We want to know what the heck is going on. Okay. And so here's a nice Earth observation fleet of the various satellites going over here. And you should see a few Landsats going over there. Okay. Let's see. And skipping. All right. There we go. So here's the Earth observation fleet as it stands right now.
Can we ask questions while you go? Or
Oh, absolutely. Yeah,
do
I
you know
encourage it.
much about the orbit, like what those are called and what it's doing?
So for Landsat, it's a near polar orbiting, near Earth polar orbit, basically. So as the Earth turns, it's going near the poles. Okay, and I believe it takes it basically goes around like every 90 minutes. Okay, and it's sun synchronous, so it's going to take its measurements pretty much, at maximum reflectance, usually between like 10 and 2 p.m. So max green effect and all that sort of
So
stuff.
it captures like a slice of the orange, and then the Earth rotates, and then it comes around and captures the next slice of the orange.
Absolutely.
Okay.
And that it's been doing that for many, many, many years. And so what we're looking at here is some of the different regions. Of course, we're looking at the forest, not the tree. And then you have other ones that are looking at, like the entire half of the Earth at the same time. So you need that sort of, I like to call it sort of a data layer sandwich where you have, all of these different satellites looking at, different aspects of the Earth through, different scales. Okay. But Landsat is 30 meters, which is about roughly the size of a baseball diamond. Okay. And so, what I derived this project from, these Stellas and all that, was basically talking about infrared remote sensing in about 5 to 10 minutes. So I talk about the EM spectrum, in this case, just visible light. All right. And of course, our sunlight is composed of all the colors of the rainbow, and our visible light is white. And then we talk about additive color mixing versus subtractive color mixing. I'm sure you all know what that is, right? So with light, if you shine light all at the same point, it gets brighter. But if you were to mix paints, different color paints all in the same point, generally speaking, it would get darker. All right. So with that being said, what color of light is being reflected to your eyes right now with this picture? Green, right? Okay. But of course, I'm a scientist. I'm a nerd. It's not enough for me to know it's green. I want to know, how green is it? How orange, how yellow, how blue, so on and so forth. Okay. And when I do that, I get a spectral signature. Okay. And so that was a sort of a sample of it. Now, as green and lovely as that plant was, and that's why I have some of these plants up here, it's reflecting near infrared about twice as much. And of course, we can't see that, but we can measure it. Okay. And why do we want to measure that? Well, we'll talk about that in half a second here. So this is the way that Landsat is going to see the Earth, and you're going to see us viewing the Earth and viewing this near infrared in just a minute. Okay. First, we're going to go and start with, and this feeds right into the additive color mixing here, red, green, and blue. okay? And we're going to view the Earth this way, and of course we can get, you know, a nice natural color image of the Earth. So this is going to be the Florida Everglades, and you're going to see, you know, Miami, and you're going to see some agriculture. And it doesn't go extremely fast on here, but at a certain point I should probably double the speed so that it goes through. But you'll also get to see some agriculture and all that, and again, the Everglades over there. And again, what you, me, regular camera would see basically if we were looking at this Earth in this day and time. Okay. And then we're going to go out into the shortwave infrared and the near infrared. Okay. And we're going to look at the Earth that way. And you're going to get to see the Earth in a different perspective. Now, this might be old hat to quite a few of you, I'm sure. But now you get to see, you know, these nice bright greens and all that. And so if we're talking about red, green, and blue, and then we mix these bands in there, where we have shortwave infrared, near infrared, and then the green band, then we get those nice bright greens, and that's right in that near infrared. Okay, so when I say it's reflecting near infrared about twice as much, that's why you're seeing this crazy neon green going on here. And then you get to see, of course, like, you know, the bare farms and all that sort of stuff over there in the agricultural district, and sort of a red. Okay, so it gives us a nice contrast. So we get to see where all this vegetation is. Now, if we do a near infrared photo, and you might be used to this one as well, okay, where near infrared is in the red, we also get some more contrast. And now you get to see a bit more of, like, you know, sort of the sediments and the effluences coming off of the Everglades there, as well as some of the shallows. And then you also get to see a nice pattern of the vegetation as well. Okay. Any questions so far? Am I going too fast?
No.
Too slow? Okay. All right. And if I'm being too boring, just let me know. So that's the onion scan, and for some reason it doesn't want to do it. So, you know, and one of the things that we do with this is, I know that you know about near infrared and all that, is why would we be looking at, you know, the near infrared in Las Vegas? What is that telling us? Any ideas? Huh?
Moisture.
Not just moisture, but what is it showing us? What are we doing over here?
Expansion.
There you go, expansion. So, but what are we bringing over here? Of course, that's showing that expansion, right? You know, humans love their plants, so they're bringing their plants. So it tells us where the humans are, and so there might be pieces in there, and this isn't the best one, but there's different pieces in there where it doesn't look like humans may have settled or whatever. It's a very sort of like out of the way, and you'll see a little dot of red, you know, where someone's got their house or whatever, just because they decided to have a plant there. So it tells us, yeah, about the human expansion. Okay. All right. And so with that near infrared, okay, and well, I'll ask you, where do you think this might be? You know, on Earth. Any ideas?
Forest.
Huh? Not a forest. See that all the center pivot irrigation and all that, and the farms and all that? Okay. So we're looking at Earth here, and we're looking at agriculture. And one of the cool things, and this is around near Kansas here. One of the cool things you can see with that near infrared, and we're going to view this again, is basically as that near infrared starts coming down, okay, that means that the plant is stressed. All right. And so the really fun part is, before it starts turning yellow, brown, or wilting or anything like that, we can measure that the plant is stressed. And so you see agriculture up here. So we're taking a look at the health of our food and what our food eats. Question?
So deeper the red, is that healthy vegetation?
It can be denser vegetation like pine and all that sort of stuff. One of the things that we'll be looking at is, say, like, you know, the spectral, basically, and I believe I do have a slide on there, the spectral characteristics of that particular location, to see if we can identify exactly what kind of species is there, and see if they help.
Speak to density.
Yeah. Health, density, and productivity. Yeah. Okay.
Mike,
Yes.
you mentioned the red is coming down. That means it's less reflecting, less infrared.
There's so when the near infrared starts to drop, so if you take a look at the same place, you know, over and over and over again around the same time and all that, and you start to see a drop in that near infrared.
Intensity.
Yeah.
You mean as far as being more or less vibrant?
So no, because the more vibrant stuff over here is usually like new growth. type of stuff over there, and that's what you're seeing over there. But the darker red, that might be a more established, denser forest, and sometimes a lot of times it'll actually be like some conifers that have like a really dense sort of look to it as well. Okay, so again, it depends on what it is. So, but if we're looking at like agriculture itself, again, you have sort of, just a homogeneous sort of, area that's, relatively new growth, and you get to see it in the stages as it goes. So you'll have a deep, dark, intense red, at like the late stage growth, and you might have a very bright, sort of vibrant, sort of red when you start out with some of the newer growth. Yes,
So, do you have to look at
Depending
it
on the
the exact
vegetation.
same day every single year, right around the same time?
Uh,
Otherwise, you're gonna get seasonal changes.
Of course, you're definitely going to get seasonal changes. There's going to be gradients throughout the day. There's a whole bunch of factors that go into all of this as well. But one of the really cool parts is that, like I said, you could identify, like, say, all the cornfields in here if you wanted to, based upon their spectral characteristics, and then see how healthy they are from each other on that particular day if you want. And so you can imagine that would be a nice boon for the farmers as well.
So for comparing these time periods for like geographies, are you using a computer to do that where it can, for pixel matching? And all
Oh,
that
yeah.
stuff? Because there's no way human you'd be able to.
Yeah, and yeah, exactly. So basically, as a human, obviously, you wouldn't be able to go to, just crop, and, just looking at the spectral characteristics. So you get the whole broad swath of the stuff, and, then you get a better estimation and all that, And again, it's still within certain degrees of certitude, of these things. And then you can start to see what's, again, going on with those crops and all that. And you can do it from year to year, from past, and all that sort of stuff. What kind of cover crops did you use, this year that worked out well, that didn't do it so well this year? And we also are able to get crop yield, basically estimates as well, from all of this.
I guess, are farmers really interested in all this data?
Oh, yeah. And they use it all the time, whether they know it or not. So I was just at a Commodity Classic, which is a big ag, basically, convention. And a lot of these folks, they'll give them like profiles of their fields. They'll sell it to them. All right. And they'll have like drone overpasses, and they might put up like a flux net or something like that, a flux tower, which is, just monitoring the farm. And so they'll do some overpasses and stuff like that. But what they're going to do is they're going to collect data from USDA, from USGS, from, NASA, from NOAA, all that sort of stuff, and sort of package it. Okay, and then give it to the farmer. Okay, and a lot of times, and again, this is where also, again, why I'm a bit biased, but Landsat is the gold standard of basically Earth observation. I like to equate it as like the sort of like the atomic clock. All right, so you need something to calibrate against, and so like you have all, like, say if you have like your cell phones and all that sort of stuff, you're going to calibrate against like the atomic clock because it's the best, right? So that's what Landsat basically is right there. So if it's the atomic clock, some of these drones and some of these other satellites, maybe they're like, Casio watches. So, any questions? I'll go on. And so basically this is sort of like, again, the live version of the intro to remote sensing sort of basically lesson that I would teach to some of the folks. Okay, and I would have them go back and forth between these and see, like, the agriculture and how they can see it. Although this one doesn't, these slides don't seem to compare as well. But like I was saying, as you go out and further into the shortwave infrared, you get to start to see the spectral profile of the different vegetation and all that. Okay, so and again, for the new people to remote sensing and all that, I would basically say it's sort of, and again, since you're astronomers, that you can tell different properties based upon the different spectra that things reflect. And this is what we're telling over here. And you can discern at this point, again, to within a certain degree of certitude, that something is corn or tulip poplar and so on and so forth based upon the way it's reflecting that light. Okay. So they do have spectral libraries where they've, obviously, just taken collections of these sorts of things. And so you'll go out and do in situ data and all that sort of stuff and start comparing it to like Landsat and to the other satellites and all that sort of stuff. Okay. But you need that data layer sandwich to go ahead and confirm, up and down the chain, that what you think you're looking at is actually what you're looking at. Okay. And so here's a bit more. And so I sort of wrap up the intro to remote sensing with these two images, because we talk about the visible, we talk about the near infrared, and then we go into the shortwave infrared, and a lot of it's conceptual, but here's another sort of application of it besides agriculture. So on the right there, you're seeing a burn scar. This is the California station fire. Okay, so this is in the regular visible, what Yumi, a regular camera would see. Then on the left, and again, you've gotten introduced to this in the Landsat onion skin that we viewed earlier. You're seeing exactly where the burn scar is and where it's very vibrant over there. You're seeing actually where the fire is. And you can see we've penetrated through the smoke and some of the atmospherics and all that sort of stuff to see the ground below. And obviously the picture on the left is going to give you a heck of a lot more information. It's going to be a lot easier to quantify and all that than the one over there on the right. And that's why we look at, basically Earth, space, big stuff, small stuff, and all these different wavelengths of the EM spectrum, because we want the whole story, and the right one just doesn't give us the whole story.
You're saying right, you mean this, that when you say right?
When
you
I
mean-
say right, my right.
You're right, okay,
Yeah,
so
yeah.
our left.
Yeah, sorry. Yeah. Like I said, either over or under caffeinated. You go ahead and judge. So that's one of the applications. And so if this plays, yeah, you're gonna see the Yellowstone, basically recovery and all that sort of stuff. The fire that happened there and then the recovery.
How does this work in conjunction with GOES,
With what?
with the GOES satellite?
With the GOES satellite? I mean,
Kind of work together, or?
oh yeah, I mean there's so many synergies that go on with like all of these different types of satellites, and so I'm not as familiar with GOES as I would be, say, with like a PACE and stuff like that, because I just haven't worked with enough with the GOES data. But again, anything that's looking at like surface reflectance, like say MODIS and all that sort of stuff, they'll go ahead and cross calibrate and all that and verify and see trends. Oh, sorry. I got kids, so I always have to check. So yeah. So, and do we have sound here by any chance?
Yeah.
Okay. And I don't know if this is going to transmit the sound. I hope so. Okay. Ooh. All right. Yeah. Let me turn that. Let's mute that because that's doing this thing. Do we have like speakers or something so it doesn't do that?
I honestly, I'm not, I've never seen it do that before.
Well, if you mute yours, you
Let me
might
mute mine.
you might mute the camera.
Yeah.
Can I have that mouse?
Okay, sure. Sorry. And so, I mean, this is a kind of a relaxing video, but it's a very good one.
I think we've lost audio online.
Sorry, we should be good now.
Awesome. I think we got this handled. That's great. Basically, as I was saying, so our friends over at ESA, they have Sentinel-2, which is sort of like their version of Landsat, if you will. Okay, and we actually have a harmonized Landsat Sentinel data product. Okay, and so that gets it down from that 8-day repeat time that I mentioned earlier down to 2 to 3 days. Okay, so you can imagine again how valuable that would be to a farmer, right? Okay. So let's see here. I'm not going to play this particular video because it's also. And then we have Landsat Next, and Landsat Next is basically, and I'll get a little bit further to that. Landsat Next is going to be a constellation of about 3 satellites. Okay, it's due to launch in 2031. It should be getting it down to a 6-day repeat time, and with our friends over at ESA, possibly down to maybe within a 24-hour period. Okay. And that's what we're hoping with that. And this is Bruce Cook, really awesome, funny guy that I to work with, and of course the Landsat Next project scientist. Okay, and Landsat Next is also going to have 26 bands. It's actually, I mean, it's going to be the next evolution in Landsat. It's going to be what remote, basically Earth observation was with ERTS or Landsat 1 is to what Landsat Next will be coming up. Okay. That makes sense. All right. Now, moving on to the educational portion of this, and again, some of the fun stuff, now that you have a bit of the background with the Landsat and what we're looking at, and some of you got to play with some of these things, which were basically analogs to Landsat. That's what they were trying to show. So you were seeing basically, the spectra coming in and all that, and the readings, okay? And so you're seeing the light, and that would be Stella, okay? Now, I got assigned to the Stella project about 3 years ago with the creator and lead engineer, Paul Morell, who started coming up with this. And basically, we were looking for something to replace some handheld spectrometers that we used to use for my infrared remote sensing. And we're like, hey, well, we have engineers, we have scientists. Let's go ahead and see if we can't develop our own. Okay, and that would be Ginger Butcher who did that. Okay, and then I got fortunate enough because I knew how to solder and all that. And she's like, hey, I don't have the bandwidth for this. Take it and run with it. Okay, and run with it I have. And so there's me at the Commodity Classic in 2024. Again, talking about agriculture and how we can see the health and all that. And again, there's there's vegetation indices and all that, and a lot of farmers know some of these, at least the names of the vegetation indices, especially something called NDVI, which is a normalized difference vegetation indice, which is basically just a ratio between the near infrared, where you know that it's high in reflectance for a healthy one, and the red absorption, where that's basically the food of the plant. Okay, and so that's a ratio, and they get to see that in real time. And so I do have hands-on things that you'll be able to play with in just a minute, and you'll be able to take a look at that. So with Stella, it's become much more than just Landsat now. And so what we like to ask for Stella is, what do you want to measure? So we've been working with other scientists and engineers, and I've talked to lots of makers and just science enthusiasts. And basically, again, they're low cost, off the shelf sensors. It's all open source. So it's very rudimentary, but it gets you an idea and you can see the data in real time. And the power of that for, a lot of folks, it's just, you can't, there's nothing like it. I can talk about Landsat until I'm blue, and I did over here, but until you actually get to see some of the numbers and stuff come in, at least for some of us, then we actually start to grasp, oh, this is what I'm looking at. This is what I'm measuring, and this is why I'm doing it. Okay. And so we have a suite of Stellas. All right. So some of you might have seen the Stella 1.1 and played around with it a little bit. Okay. And that's what you were looking at over there. And again, that's an analog to Landsat. So it's basically what we call VNIR, or you have visible and near infrared light. And this one's actually got a thermal on there. Okay. And some of you saw the little dot up there, the 940 nanometers, and that's basically the LiDAR. Okay, measuring the distance from thing to thing. Okay, there's also a bunch of other stuff it takes on there, like barometric pressure, relative humidity, stuff like this. Okay, one of the ultimate goals with that is to eventually do basically evapotranspiration. Okay, and so measuring the amount of water coming off of these plants and all that, off of these things. And Landsat does that. And if you look back there, there's actually a sheet called Open ET, and you can take a look. And if you want to look in your backyard over here or whatever and see how much evapotranspiration is coming off of there, you can do that. That's pretty sweet. All right. Well, we're developing that, and then along came Dr. Nissa Rain, okay, and she's like, "Can you make something like this for air quality?" Okay, and Paul Morrell, if you ever get to know the guy, literally as you're talking to him, he's building these types of instruments in his head and mapping it out and diagramming it because it's sort of his passion. And so he started building this instrument. That one measures particulates in the 2.5 and the 10, CO2, and again, barometric pressure and relative humidity and all that. Okay, and that one doesn't require any soldering or 3D printing. Okay, and we have quite a few of those that don't require soldering or 3D printing. The next one is the heliophysics. So the heliophysics people, I met up with another engineer, okay, on the lawn, and he's like, "Hey, you know, I know that instrument. That's a Paul Morrell original. I've worked with him before." And I'm like, "Yes, it is. Let's have a meeting." We met up with him. His name is Pat Huss and Alana Resnick. And basically, again, right there, we were like, "Well, can you add this on there? Can you possibly put something like this on there? What do you think about this?" And so we came up with the heliocell. Okay. And so that right there is a half of a ping pong ball as a diffuser. Okay. And I'd say one of the best meetings I ever had was them actually trying to get the spectral profile of the ping pong ball, was them discussing how to do it. They needed to flatten it, and they wanted to do that without compromising basically its material structure. And it was like 2 or 3 engineers and scientists, and I wish I had recorded it. And so from then on, I've started recording every meeting because, again, fascinating. I could just sat there and listen to them talk forever about it. Okay. And so I'm just going to show you sort of like the development phase of this thing. Okay. And we're doing it in terms of Landsat. Okay. So phase A is the planning. Okay. Again, how do we make an affordable, easy to use, basically instrument that gets you, quality data while, again, still making it affordable for anyone, anywhere to be able to put together. Okay. And so we started work on the Stella 1.1. Okay. And this was the original, the 1.0 here. And again, this is all open source. So you can you can get all of this stuff. You can get the schematics, you get, the parts list, step by step, how to build it, how to collect the data, and then how to analyze the data. Okay. And so then, we're like, well, we need something to do with that data once we collect it. So we do have an online data viewer and analyzer. Okay. And what you get to do with this one and what you're seeing over here is me having collected data from a full sun atrium. Okay. And now you're collecting the data, and the data is coming in as irradiance. And so we need to convert it to reflectance. So we do that by calibrating it, and we're, instead of Spectralon, which costs usually thousands of dollars and is, basically like as close as we get to sort of like a perfect Lambertian surface. At the moment, it's made out of Teflon and all that. We're using polystyrene foam, which is about, like $2 a sheet, $5. You want the bumpy kind, you don't want the smooth kind. And it gets you about 95% of what Spectralon does. Okay. So again, trying to make it affordable. All right. So we do calibration, and then we can do the vegetation indices. And I just talked about NDVI, and NDVI is right up there. And so what you're seeing with the NDVI and the ratio over there, okay, is as you're getting closer to 1, that's denser, healthier, more productive vegetation. Now, as I was going along, and this goes over time, you're starting to see dips in that NDVI. And the closer it gets to 0, basically that indicates bare ground. Okay. If it starts going into the negatives, that usually means water. All right. So you're seeing me go across this vegetation, and it was sort of like, rocks or whatever, it was very tastefully sort of put together and all that. So it's sitting there baking in the sun. So as I go across, okay, you start to see some gaps and dips in that NDVI. Now, down below there, we have, we're also taking measurements of ambient air temperature and surface temperature. And so you're getting to see where the diffs, those correlations, basically with the diffs in there to the surface temperature rising. So if you're talking about UHI or urban heat island effects, you can start, taking a look at that as well. Okay. So this is part of the team that we have going on here. All right. And, it's been quite a process. Right now, we're in sort of a transition period coming out from under Landsat, and because we are multidisciplinary and all that. So some of these folks are still with us, but they're not, contributing quite as much. Paige Williams, for instance, just got her doctorate, so she was gone for about like 6 months, doing her stuff to get her doctorate and all that. But we did field testing. You can see Dr. Petya Campbell over here. She is the lady with the clipboard. She is a forester, okay, and she's the lead scientist basically for our team. Paul Moreau, he is the creator and lead engineer there, bending over, and they're actually looking on a tablet of Spectralon, because we're doing comparisons between Spectralon and the polystyrene, as well as, and then back and forth with like the grass and all that. That is also bending over there is Jesse Barber, who is our physicist and calibration and validation guy. Okay. And so he's down there, and we also have I believe he's got a Stella too. But we also had a field spec out there. And if you don't know what a field spec is, it is also a spectrometer, kind of like this, of much, much higher quality. And they also cost about $250,000. Okay. So basically sort of the next step up from, say, like one of those Stellas would be a few grand at the very least for, a quality spectrometer. Over here, Ross Walter, he is the guy who developed the data viewer. Okay. Dr. Nissa Renning, I told you about air quality. Dr. Paige Williams here, she's been flying these on drones with her students, okay, for about 1.5 years. And she's got her whole hexacopter with a hyperspectral and a LiDAR, and she's doing what we call BRDF, bidirectional reflectance difference. I'm forgetting the last portion of the acronym, function or something like that. Anyway, but basically, you got different shapes with all these different vegetation and from different angles and all that. They look different, and she's mapping all of that sort of stuff out to get us a better, basically, surface reflectance data from that. Okay. Okay. So we launched the Commodity Classic. You already know that, and I don't know why it's bleeding.
Excuse me, we do have a question on the chat.
Yeah, what's the question?
Yeah, Harini asks, can the Stella be used on Earth or only in space?
Huh? Oh, it's used on Earth. Yeah. So Stella's, so I'm using the Stellas on Earth. So I actually have a few folks here that actually started playing around with the Stellas as I was walking in. Okay. And so.
Thank you.
Yeah, no problem. We're also going to get into some other fun stuff that you are going to be very interested in just a minute. But we got 2 high school juniors. These 2 high school juniors built 40 of those spectrometers, okay, over a 10-week period. Okay. They actually beat it by 8 weeks. We went out and we did circuits, basically, of taking measurements and all that, because we were comparing them, at least 2 field measurements per unit. And that means a round of them going to like forest to asphalt to concrete, all this sort of stuff, as well as, of course, calibrating. Okay. And they just actually got scooped up by and I don't know the name of the instrumentation firm, but basically they do high-end instrumentation, because they knew about like the troubleshooting. They knew about, taking the measurements. They knew about the sensors and all of that. And I just happened to be in a meeting at SSAI with it, and they only take 2 students a year. They're in college now. And I told them about this, and like, send me all of their information. I want them immediately. And so now they're going to get to work on some multi-million-dollar instruments because of the knowledge they've gained. Okay. With the RAC team over here, it's also transdisciplinary. So one of the things that they asked is what they could do with these things. All right. And what they could help us out with. And we told them we need some technical and scientific manuals. Now, you can imagine all of the different sort of disciplines that actually feed into that, right? You have graphics artists, you have, outreach folks, you have, English majors, you have all of these different folks feeding into this. Okay. Dr. Huichimangaro Campos down here, he's from Puebla, Mexico. Okay. They don't have money for a field spec. He cold contacted us on our GitHub site, which is our sort of community forum, and let us know that he and his undergraduate students are using them. He never thought he'd be able to, and they actually have them on the on the paint stick at that point. They had the Q2s, which I'll mention a bit more in a bit. And they're doing principal component analyses on broadleaf species down there. Okay. And so I want to take that and I want to develop that into, what's good data versus bad data. What's the need for calibration and all that sort of stuff. Okay. So, I don't want it to play any of these. I just want to move on to the next slide. There you go. Okay. So here's some more Stella in the classroom. There's Paige. How am I doing on time?
You're
Okay. I don't want to.
another 15 maybe, or?
Okay. So, like I said, we've had them on drones. They're very lightweight, they're very adaptable. So you put them on a quadcopter and again, start doing your own thing with it. We have drone housings. This is one of the older models. So we actually have a newer one that weighs less and performs a bit better. We've been out in the field. Okay. Been comparing it to, again, field specs and all of that. And I'm going to zip through it a little bit faster just so that we get more time for Q&A and all that sort of stuff. And you all get to at least play with some of these things a bit. Okay. We've been working on the calibration. One of the really cool things is, and I mentioned it to a few folks earlier, we had a graduate student who did her master's thesis using one of these from Rochester Institute of Technology, which is, quite a prestigious spectroscopy and optics school. And she's helping us out doing basically field calibration, classroom calibration, so that anyone anywhere in the world can start establishing some error bars using low cost technologies. Okay. And so you get to see some of the data viewer and some of the Stella AQ and all that. That's her right there in the lower corner that we're working with. And she's pointing out stuff. There's a gentleman up there, Aiden. He was doing mosquito mapping and he was using the Globe basically observer app, which if you don't know about Globe, you can literally start doing citizen science on your phone with the Globe citizen science tool. Okay. And we're talking about like looking at clouds, looking at, again, the Earth in various different ways. Okay. And so this current suite of Stellas, we've actually expanded. Okay. And then you also get to see the interns over here doing some more of their stuff with, and again, Jesse Barber over there with the Stella. He looks sort of like a Ghostbuster. He's got a big backpack on. Again, it costs like $250,000 the thing. So you're not going to trust that with your junior, basically junior high schoolers, doing the field spec. But so he got to wear that.
So they can compare the Stella results to the high-end results.
That's and see how in
agreement or.
I mean, again, it's not going to be one for one. We were also seeing some disparity, especially like I believe it was in the 730 and 760, and the speculation from our Dr. Petra Campbell was basically one of the reasons is because the field spec is pointing straight nadir, and the Stellas, because they were on the poles that they were pointed at somewhat of an angle. Okay, so we have to test that, but it is really cool that you even get something that's close. So here's sort of the wrap up, the Stella website and stuff, so you can go and check them out yourself. If you go to the first website, it's under Landsat, so you're just going to see the spectrometers. But if you go to the GitHub, you also get to see the heliophysics, and you'll also get to see the air quality. Now, I've been talking about some of this stuff, and I have some of them with me, so you can play with them. I also have the 1.2. Now, I don't know if the camera can see me, but I'll show what I can over here.
Let's turn the lights on.
Okay. And we just developed something new. And again, we were talking astronomy and all that. Well, first, I guess you know what? I'm going to start talking about this guy. So this heliophysics one, again, we have a Stella Astro group. All right. And in that Astro group, there's this person named Chris White. And he was telling us, and they work with parks a lot. And I was just out and actually at the Staunton River Dark Sky Park not terribly long ago. But their idea was to put these up on the building, so we have the housing for that. you know, so that it's a bit more rugged than this. And they want to look at light pollution. Okay, north, south, east, west. All right, and because there's like, you know, different types of LEDs and incandescents and all that sort of stuff, discerning those, we might be able to do that with this, because one of our satellites, Veneer, or not Veneer, Veers, is having trouble, basically discerning those types of lights. So we can actually try and do some fun, again, citizen science, and start to see where these lights are coming, you know, what kind of, what they're comprised of. Okay, so that's one thing. One of the newer things, and we're working with a group of retired scientists and engineers down in Florida, Sarasota, Florida, and they're put on an informal program called Coastwise. They're interested in looking at harmful algal blooms. They want to look at it from drones. They want to find out where they start. Okay, and they love these Stellas, and they've had some students starting to build these and work with these and all that, as well as taking, of course, like, you know, spectral measurements of the plants and stuff down there for a spectral library, but they needed more granular data. So our engineer came up with this guy here. Let me show you. Now this is a cheap $40 Celestron telescope, okay, a Newtonian one, and it does not have a mirror, or no, doesn't have glass in there, so that you still get some of the near infrared. Okay. Now you can. We just came up with an adapter, and now this can go on any telescope. Okay. I did it wrong again because there we go. Okay. Okay. Now this is an 18 band, basically multispectral sensor here from 410 to 940 nanometers. Okay, 20 nanometers full with half max. Generally speaking, it'd have a plus 20 to a minus 20 degree field of view on here. And with this, I believe it gets it down to a 1 degree. Okay. And so you can get some more granular data. Now, of course, we can pump this up. Okay. And so, and you can put it on your telescopes if you wanted to. Okay. And start getting some properties. We were just talking with the guy right now, this morning, and he's an undergraduate and he wants to use one of these things for his, basically for his thesis to graduate. They require that there. And he wanted to throw a prism on here. Okay. And start, you know, just basically selective for the different bands or the different nanometers.
What was he going to look at planets, or did he say what he was going to look at?
He was not really.
Okay.
No, I mean, he was just very interested in doing, you know, having some fun with it. He was a physicist, so he was, you know, going off on so many tangents. Okay. Just like I might. But you can also put it on microscope. So one of the other things that we were thinking about as well, you know, because you sort of stain like some bacteria or whatever, is getting a count of, say, like that bacteria, you know, based upon the amount of light that it's, you know, basically letting on for stuff like that. So you can do a bunch of fun things. Now, eventually, and again, we're trying to make this all hierarchical and all that sort of stuff. We're looking at putting a hyperspectral on here at a certain point. Okay. And it would about double the cost. But again, as soon as you start knowing something a bit about, you know, like the regular spectral data and all that, and you're like, hey, I want to put a little bit more money in this, you can do that. Now, here's where it becomes really cool. And somewhat science fiction around here. Okay. We have the Stella 1.2. Okay. This is a module base here. Okay. This one has the ability for GPS, Wi-Fi, all that sort of stuff. And again, we're trying to keep this all low cost, so about under $200. All right.
You should call that one the tricorder.
Tricorder, right? That's the same, tricorder.
It's like we can't go quite there yet. So again, 18 band spectrometer, surface temperature. Okay, 4-meter lidar on here. We also have a 40-meter lidar. And this also has a cuvette, basically holster there, so you can do liquid spectroscopy. We have one for the 1.1 as well. Okay. And so now you can start getting basically, you know, all of your fun data on here. And you're good. All of it comes down on SD cards. as .csv files. Okay, so you can do all the fun spreadsheet math you want. And now you can change it up. CO2, you got the little nose here, that's methane, particulates, barometric pressure, all the fun stuff over here, and now you have an air quality instrument. Okay,
You use that in mining at all?
what's that?
Is that used by miners at all?
By mine, oh, by,
Not
those types of
miners.
miners. Yeah. Hold on a second.
You have to be 18.
Yeah, exactly. Not to my knowledge.
Okay.
Okay, but we are talking with some fun.
Canary in the coal mine kind of thing.
Yeah, right. That would be nice. Yeah, and well, and again, we might put on some different sniffers on there as well. And so we have ideas for that. And that's where this thing comes in. Okay, this is the expansion module. This is a build it and test it yourself. So we're going to have a suite of basically low-cost sensors that you could choose from. Okay, and you start to learn how to build your own instrument. You start to test your own instrument. Okay, and you can imagine, obviously, for educational purposes, that's fantastic because you're like, what do you want to measure? Okay, now build your instrument. Now test your instrument. How good is the data? How bad is the data? Why'd you choose this sensor? You just got tons of questions, but they get to build it and then say, okay, now if you've got the sensor package that you like, now you can build out, your own 3D printed thing. So you're combining multiple different disciplines. Okay. So, like I said, all of this stuff is available online, so anyone, anywhere can do it. It's all open source. Okay.
So for HAL members, if I could, so for HAL members, if there's I see a young HAL member in the room right now. And if there's any young HAL members online who are interested in this, then, reach out to me and maybe the club can help, we can purchase one of these for the club and you guys, can use it or do some citizen science or reach out if you're interested in doing something.
Yeah.
With this.
And again, some of these can be combined. So for instance, you got obviously the heliophysics one, incoming solar radiation, reflected, basically radiation, right? And then of course, if you put it in, say, an enclosure, that's one of the fun things we were looking at with plants and all that. Okay, you can also use the air quality one and you can get like respiration of the vegetation as well. Okay, and so it can come full circle. And then again, I was also out at the Commodity Classic, okay, and just demonstrating, to the farmers why they would want to measure something like this. There's a lot of them, of course, over the like 2-week period or whatever where those fires were going on, obviously they didn't have as much solar radiation coming in, and they were telling me they delayed their harvest by about 2 weeks. And so I was just passing this over this thing to sort of simulate like the clouds and the amount of solar radiation coming in and all that. And again, it's a great demonstration because you get to see the little screen here, okay, and you get to see like where it drops off and all that. And of course, it's all being recorded on a data recorder here as well, and so you really get to have some fun with it. Our engineer, for instance, was in the totality of the eclipse, okay, and he wanted to see if any UV was scattering, all right, and he was out there, and what we were measuring, at least with this sensor, is that there was no scattering, okay, and then of course you get to see the different spectra and how they drop off over time and all that sort of stuff. And then which ones come back first and so on and so forth. Very interesting stuff. Any questions? Yeah.
So you mentioned people can build their own
Yes.
Stella 1.1 or whatever. Is that by going to the website and then you get a list of materials and where to order those materials? Or is it a kit or?
So we're looking at people for kitting it at the moment, okay? And we can't endorse any one vendor. So we give you the parts list, okay? And then step by step how to build it, okay? And then and I have videos on how to use some of these types of things. And we're aiming to put more out there as well. And there's build videos too. So like, for instance, 3 of these, the air quality one, the heliophysics, and the Q2 do not require any soldering. You don't even have to 3D print. We have printouts where you can just lay this on a piece of construction or a piece of cardboard and actually just start building this. And like I said, this is a half of a ping pong ball. Here's a diffuser. So, again, trying to make it cheap, easy. All the print files are online as well. So you can start printing that out, anytime you want. The Q2 that you see over here, this is actually a drone housing. Okay, now it's a very simple thing. It doesn't have the surface temperature and the LiDAR on there, but it does have the 18-band spectrometer. And I use this when I talk to lawmakers. Okay, because right here you have the visible portion of the spectrum on this side, and then you have the near infrared on this side. And again, you all are in the know, but a lot of people just don't understand that you can measure stuff with light and that it tells you something. Okay. And so once they see it, seeing is believing. And then they're like, they skip past pretty much, all the skepticism, and they're like, what else are you measuring? And that's when I laid the Landsat benefits book on them. I'm like, these are just a few of the various areas. One of them, of course, being agriculture, which again, all of them are interesting. So that's why we usually dip into that well so much. Any questions? Any other? Yeah.
So I think you said it was the heliophysics sensor that's measuring light pollution.
Yep. Yeah.
So do they have a way to convert that to like model ratings as well? Do they have any algorithms or software that you can say this much light pollution equals this model rating in this particular area?
You're out of my wheelhouse for that particular one. So I'd refer you to our heliophysics specialist who would be on the resume. And again, one of the ideas for this as well is to actually, again, grow that sort of team and have those ambassadors. So we have like the air quality specialist, heliophysics specialist, an astro specialist. Right now, we're working with a guy who's doing agriscience, and he also does astronomy. Okay. And so he was massively interested in this. So he's developing a whole astronomy course in this type of stuff as well as an agri-science curricula. His actually job is developing curricula. Okay. And then we have people who want to take it underwater, and we've had stuff there. So
All right, if there's any other questions, maybe we can ask them at the end of the meeting. I'd like to say thank you to our speakers. And will these things be out so we can play with them at the end?
Yeah, you can
So
play with them.
looks like we've got some plants and stuff. We can maybe actually measure some things in real time.
Benefit of being here in person.
Yeah. I wanna look at these plants with this and see the change in the colors.
I was gonna look at Jim's beard.
Let's see. Get the important stuff.
Okay, again, I'd like to say thanks. That was really quite interesting. I appreciate the presentation. I'm gonna go ahead and start sharing again. Messed up now that I dropped the
While you're waiting, I should mention that we have a chance to put some of these on Artemis. So that's one of the things that we're doing as well.
I'll tell you what, Zoom, things move all, the menu bar moves all over the place. Where the heck did the thing go? There you go. Sorry, people online, I'm just getting it together here. Okay, can you guys see my screen now? Online?
Yep.
Yes.
Sorry for that. Okay, so let's move on. We have two more of our regular features. We've got Jim with his shallow sky stuff. Jim is actually in the room to prepare. So you want to go ahead?
All right, so running down the planets, Mercury actually is a pre-dawn object this weekend. Not one of the greatest appearances because it's going to be low down in Sagittarius, but still worth a shot. Whoops. Venus is in the morning sky very early. So if you're an early riser, you're out to work early, you'll catch that nice bright beacon in the east. Mars is in the evening sky, but really challenging, very tiny disk, mainly just a photography object. Jupiter is going to be heading to a solar conjunction soon. So if you want to see Jupiter, target it as soon as it gets dark. Saturn is just emerging from the dawn. It's getting past solar conjunction. And at this point, you don't see any of the rings, or if you do, it's going to be an incredibly thin line across it. Lyrid meteor shower is going to happen the night of April 21st. There will be a full moon, but this one is especially known for fireballs. So you might get lucky and, a fireball is certainly going to be visible, moon or not. Not a prolific shower, but can definitely throw you some really neat, bright fireballs. And we've been saying this for over a year now, but there is Nova T Corona Borealis, and that could flare up at any time. Keep alert to your favorite astro news source for that. Next. So a lot of times it's when planets or brighter objects which move through the zodiac, the ecliptic, they can come across a particularly interesting object, and it allows you as a beginner to kind of find that object that you might have trouble finding from around here. And it also provides a really cool thing to look at with binoculars or your telescope. So such an event is going to happen on May the 4th. Mars, it's a lot dimmer than it was a couple months ago, but it's still at first magnitude. It's going to go by a very pretty open cluster called M44. It's only one of two negative eye clusters in the ecliptic, so it can have solar system visitors, the other one being the Pleiades. So again, it's going to be, if it's clear that night, get your binoculars out, go take a look at Mars and catch the beehive right next to it. Next. And surprise, we have a morning comet. There is Comet Swan, which is in the morning sky. It's going to reach perihelion, which is closest point to the sun, on May 1st. Could be getting up to third magnitude. Comets are notorious for being unpredictable. I think David Levy said they're like cats. They do what they want and have tails. It's going to be a horizon hugger, so it's not going to get very tall. It's not going to get very high. You're going to need a good northeastern horizon. It's going to be running through Andromeda and Pegasus. Should definitely be visible in binoculars or a small telescope. One more click for a chart, Victor. There we go. So again, these sort of charts are available online at Sky and Telescope or Astronomy. And it's going to be coming out of this great square of Pegasus and running through Andromeda. So get yourself a good morning northeast horizon and see if you can pick this thing up.
Awesome.
We'll do it.
Thank you so much. And next we have Wayne, who's going to talk about what's up in space. And Wayne, take your time. We don't have that many astro photos to show this month. So
Okay. Just one brief second. Okay, so we all enjoy looking at pretty pictures from Hubble, Webb, Euclid, ground-based telescopes, etc. But in particular with the space telescopes, it's important to remember that even though the pictures are pretty, the main purpose of the missions is to do science. So tonight, I hope to show a pretty picture from Hubble and talk about the science the picture was used for, and thus capture both aspects of this exciting mission. So the presentation may get a little bit technical because it's based on a professional astronomy paper that was published. So you might have to pay attention a little bit. So a little bit about the history of collisional ring galaxies, or CRGs. They've been known since about 1940 when Fritz Zwicky identified the Cartwheel Galaxy in 1941, and there's a Hubble image of the Cartwheel Galaxy here on the right-hand side of the slide. And at that point, you know, they just kind of cataloged them when they found them. And in the mid 1970s, as computers got better, there was initial theoretical explanations for their structure. And the basic result of all of that is that an impacting small galaxy falls through the center of a more massive disk galaxy. And the gravitational disturbance of that impacting small galaxy causes rings of star formation to be created as the gas is swept up in the induced density perturbation. So remember, gravity moves at the speed of light. So as the impactor falls through the center of the galaxy, that the gravitational impact just moves outward. And that causes gas to get swept up in the changing gravitational potential, and can produce star formation. Studying collisional ring galaxies helps us to understand galaxy evolution and structure. In particular, the galaxies allow us to probe the gravitational field of the galaxy that got hit. It also tells us something and we can learn about density wave physics, which is how spiral arms are formed in galaxies, among other things. And it could be involved in the production of something known as giant low surface brightness galaxies. Okay, so collisional ring galaxies are important on at least a number of different ways. So next slide.
I'm coming.
I'm sorry. Next slide.
Yeah, sorry.
Here we go.
Sorry. Tech support.
So this galaxy, LEDA 1313424, it's the last time you heard me say that, was discovered by Pasha and collaborators from something called the Dark Energy Spectroscopic Imaging Legacy Survey, or DESI Legacy Survey. So the picture they got from Hubble is on the right, and this was taken with the Hubble Space Telescope's advanced camera for surveys and the wide field channel of the advanced camera for surveys in the blue and the I bands, the B and I bands. So it's kind of an HOO kind of an image, okay? And it's a really pretty picture. You can see the main galaxy there in the center. It's actually very, very large. I hope you can see it. I can see it on my screen. There's a ring, a very faint ring of stars formed off to the left. At that bright star is in the middle of a ring of star formation. And so, and then there's these other rings, and this is important because observationally confirming the formation theories of collisional ring galaxies has been hampered because they hadn't seen any of these galaxies that had more than 2 or 3 rings, which doesn't give you enough rings to help you distinguish between the formation theories. And this particular galaxy, they've identified 9 rings. So this is a really important galaxy for the study of collisional ring galaxies and how they're formed. This image, this Hubble image, is about 4,000 seconds of total exposure time. And down in the lower left, I want you to see the scale. Okay, so that white line is 36 arc seconds long, which at the distance of this galaxy represents about 100,000 light years. Now put on your little memory hat here, and remember the diameter of the Milky Way galaxy is about 100,000 light years. So the Milky Way galaxy from one side all the way to the other is about the same length as that bar, that little white line. So this is a very, very large galaxy. So
Also, hey, Wayne, also, like on all of our telescopes, 36 arc seconds is, 15 or 18 pixels or something like that.
yeah, or 72 on my telescope.
Yeah. But now you know why we can't get pictures like Hubble.
Nope. So this galaxy, which they're calling the Bullseye Galaxy, and that's how I'll refer to it in the rest of this talk, is located at a redshift of 0.04, which places it at a distance of about 174 megaparsecs, assuming a Hubble constant of 70 kilometers per second per megaparsec. It is slightly inclined to our line of sight, and as you can see, there are rings, multiple rings seen in these images. And in fact, in this image, plus some other ground data, they've identified 9 rings, 8 of them on this image, and a 10th ring is actually inferred from comparing with the theories. They've also identified the likely impactor. They identified it by the fact that the spectroscopy shows that it's at the same redshift as the Bullseye Galaxy, so they're very close to the same distance away. The galaxy has abnormally high star formation, as indicated by lots of hot blue stars, and there seems to be a trail of gas between it and the Bullseye galaxies, like gas being dragged along after the impacting galaxy has passed through the Bullseye galaxy. And if you haven't figured it out yet, it's that blue clumpy galaxy just to the left of the Bullseye galaxy. That's the one they have identified as the impactor. Okay. So next. So the observations, the Hubble observations, were used to identify 8 rings in this galaxy, and they did this by doing an unsharp mask on the Hubble image, and which enhances small scale structures. And the image to the right is that unsharp masked image. And if you look closely at it, you can see there are some red lines drawn on it, and those show the ellipses. Those show the rings that these authors have identified in the galaxy. Some of the ellipses, they only fit to an arc of the ring because there was contamination and it wasn't clear all the way around. And using this process, they just literally used their eye and placed ellipses on it and moved them around, changed their shapes a little bit until they got the best fit that they could by eye. And they identified 8 rings using this technique. There's a 9th ring that's been identified through deep imaging with ground-based telescope, specifically the Dragonfly telephoto array at New Mexico Skies, which uses 24 Canon 400 millimeter lenses operating at f2.8 and S-Big cameras, CCD cameras, and they were mounted on an S-Big Paramount ME. So basically, it's a big array of a bunch of amateur type equipment. They have 2 camera arrays exist, each with 24 lenses and cameras. So it's important. So the rings are separated by larger amounts at larger distances. Now what they mean by that is that the radius of each ring is bigger relative to the radius of the ring inside of it. That is, the distance between the rings gets bigger as you go farther out in the galaxy. And in this image, you can see the inner rings are actually kind of piled together and perhaps merging.
Hey, Wayne,
Yes.
question for you. If you were to, if the operators of the very large arrays of radio telescopes, and they focus it on there, would they be able to pick up those rings, or are they outside the wavelength?
I honestly don't know for sure. I know they can see star formation regions in the radio, but I don't know if this is going to be, if they're going to be sensitive enough to see these. But that's a good question. I wish I had the answer.
Yeah.
Okay, next slide. Okay, here comes the theory. An astronomer by the name of Curtis Struck back in 2010 published a paper on an analytical model of collisional ring galaxies, and it's a very simple model, and it assumes a whole bunch of stuff, including, first of all, that the collision is perpendicular to the disk galaxy. That is, the little galaxy is coming in directly perpendicular to the plane of the disk galaxy, and it passes right through the center of that disk galaxy. The impact, it also assumes that the impactor is moving quickly so that the gravitational disturbance is of short duration relative to the reaction time of the target disk properties. That is, the interaction is considered to be an impulse. It's like, instead of pushing on a wall, it's like hitting it with your hand. The results you get out of that are very different. They also assume that the disk galaxy, the one that's being hit, has a flat rotation curve. This is very common in spiral galaxies, and it's indicative that the galaxy has a massive halo in order to support the high rotation speeds out at large radii. They also didn't include any gas dynamics, so they're only looking at the stars. Okay. And the basic result from this analytical model is the ratio of the radii of selectively produced rings. They have a very simple equation. I love equations. And so basically, the first ring is ring 1. The first ring that's formed is ring 1, and it propagates outward. The next ring that forms is ring 2, and it propagates outward behind the first ring, and 3 follows, it propagates outward behind ring 2, and so on. And the theory here, the model, gives us the ratios of the successive rings. So with this very simple relationship, the radius of the ith ring, say 1, to the radius of the I plus 1 ring, say 2, is just 2 times I plus 1 divided by 2 times I minus 1. Very simple. So the ratio of ring 1 to 2 is 3.0. The ratio of ring 2 to ring 3 is 1.67. And the ratio of ring 3 to ring 4 is 1.4, and so on. So it's very simple calculation. And once you've measured your rings, you can form these ratios very quickly. You don't have to convert them to parsecs or kiloparsecs or anything like that, miles, whatever unit you want to use. You can do it in pixels, and they did it in pixels. In fact, the 2 outermost visible rings in the HST rim image have a radius ratio of 1.4. which suggests that the outermost ring is actually the 3rd ring formed in the system. Okay. Everybody got that? So remember these ratios. These ratios are going to be important right now. Next slide. So buckle up. This one's going to be a little bit complicated. So let's look at the plot over on the right. This plot shows on the x-axis the predicted semi-major axis in pixels. And the y-axis shows the measured semi-major axis in pixels. And both axes have logarithmic scales. Okay, so the big tick marks are not 1 apart or 5 apart. They're actually a factor of 10 apart. Okay, so on the x-axis, that leftmost heavy tick mark is 1,000. I'm sorry, is 100. And the rightmost tick mark is 1,000 pixels. Okay, so these are large images, and the rings span these from like 200 to about 1,000 pixels in radius. Okay. Note also that the center of the galaxy is off on the lower left in this plot. Okay, since it's a log plot, it's infinitely far away on the plot, but you know what I mean. It's to the lower left. So if you move right and up, you're going farther out in the galaxy. And remember, what the observations are the measured semi-major axis. radius. That's the radius of the ring. And so what we know the Y values, we don't know the X values. Okay, so the other aspect that's an issue here is we don't know what to expect the ring radii to be on this galaxy. All we know are the ratio of adjacent rings, the ratio of the radii of adjacent rings. So that makes it a little trickier to do. And the way we do it is you start making some assumptions. And so we're going to take it a piece at a time, and hopefully we'll get through it. So first of all, the black open circles are their measured radii, and they are plotted in a specific way that we'll get to eventually, with their radius measured on the Y direction is what they measured, okay? So those are the measured points. But right now, let's just look at the one I've labeled, and I added this label, the one that's labeled outermost HST ring. This is the best measured ring they have. And so they said, let's assume that its predicted semi-major axis is equal to our measured semi-major axis. Okay. So and that's where they plotted it. It's in the same place on both axes. Okay. That's probably a good approach because it's the best measurement they had. So now, if you look at the outermost HST ring, and now just look at the black dashed line that goes through it, okay, starts up there near the point labeled ring 2 and goes down to the point labeled ring 10, okay, that line represents the points where the measured semi-major axis is equal to the predicted semi-major axis, okay? It's got a slope of 1, and so it's kind of a unity line. Okay. Told you this was going to get complicated. So now we've got to start making some actual assumptions. We do not know what ring formed first. So let's assume that the outermost HST ring is the first formed ring in the system because we don't have any information to help us. If we do that, that means it's the farthest out from the center of the galaxy. And we also know that the ratio of its radius to the second ring formed is a factor of 3. It's 3 times bigger than the second ring. So if you assume that the outermost HST ring is got measured axis is its predicted axis, that means the second ring, and it's the first ring formed, the second ring formed has a radius that's 1/3. And if you follow the blue line off to the left, you can see a little square. And they plotted that at the predicted semi-major axis, but with the measured axis, semi-major axis for the second ring that they measured, the ring just inside the outermost HST ring. If you do that with all the other 7 rings they measure, you get that blue line that ends off down at ring 8, way off to the side. Okay, so that's where you would expect them to be. The data points to be. Okay, so that's one assumption. This next assumption is, hey, maybe the outermost HST ring is ring 2. And if you do that, first of all, you know the ring 1 has got to be 3 times larger, and you end up with that data point up at the top right, where they've got it placed it on the y-axis using the outermost ring that they found. I think I skipped through something or there. Anyway, so, and then you get the kind of salmon colored, peach colored line that ends up down on the lower left at ring 9. If you then assume, so that's the second assumption. The third assumption is that that outermost HST ring is ring 3. And here they didn't actually go through plotting it because it falls right along the unity line, and you can see all the data points. Then if you assume the outermost HST ring is ring 3, the other rings they had measurements for, we lost you online. Roger West is now the host, it said. Victor, can you hear me?
Hey Wayne, Victor's computer disconnected for a moment. He's connecting back right now.
Okay.
Yeah, but we cannot hear you on the thing.
Ah, here it comes.
Okay, it seems that it.
Sorry, my battery died. We're back now here in the conference room.
Okay, can you hear me?
Yes, sir.
Okay.
We are kind of running out of time though, Wayne. Sorry.
Oh, goodness. Okay. We'll get through it quickly.
Are you ready for me to move on?
We're not seeing anything, or I'm not seeing anything. Have you
Oh,
shared?
Here we see you, Wayne. That's it.
Are you sharing your screen?
Sorry.
Here it comes. Okay, so as you can see, the data points fall along that unity line, which is strong evidence that the outermost ring is the third ring that was formed in the system. And you can continue making the assumptions, and that's what the other lines are on there. You can assume it's the fourth ring, and you'll get the gray line. And if you assume it's the fifth ring, you'll get the teal line. Next slide. That was the complicated one, mostly. Okay, as far as getting the impactor galaxy, they took data with the Keck telescope, spectral data, and you can see the diagram at the right. They've got an image at the middle, and all the white squares show regions where they did spectroscopy. And there's lines joining each of those little white boxes to a spectrum. And they use the spectrum then to analyze the dynamics of the system. In particular, if you look at, say, spectrum I off to the left, you can see two main peaks. The peak on the right is the red-shifted H alpha from the impactor galaxy, and that peak to the left with a blue dash line is the red-shifted H alpha from the bullseye galaxy. And you can follow that. Those vertical lines are the same place in each plot, and you can see that the spectra looks very different. The asymmetrical spectral lines, like over in number C up in the top right, they interpret that as H alpha emission from gas streaming from the impacting galaxy to the galaxy that was impacted, which is strong evidence that that is indeed the impacting galaxy. The impacting galaxy is moving at a velocity of about 705 kilometers per second relative to the bullseye galaxy. And basically, all these observations are consistent with a collision approximately 56 million years ago. And that's consistent with simulations that show that rings are visible between 50 and 150 million years after a collision. So next. As far as the giant low surface brightness galaxies go, on the right is an image of a galaxy. It's a negative image. This is not the bullseye galaxy. It's a different galaxy. And then the contours show the radio distribution of neutral hydrogen. So there's really a lot of neutral hydrogen far outside the visible portion of this galaxy, implying that there's mass and stuff out there. Okay. So the formation of these giant low surface brightness galaxies is not well understood, but central collisions like the bullseye galaxy might provide clues as to their formation. In fact, colliding collisional ring galaxies, sorry, got all too many acronyms. Collisional ring galaxies may be a formation method for these galaxies. Okay. Why don't we go to the final slide because we are running out of time. I apologize. So here's some, no, go back one. Here's some resources. These are all professional papers that I used to look at this. But basically, we've gone from a beautiful image of a galaxy taken by HST. They've made some simple measurements from it by eye, as well as some additional observation with other facilities, and they applied a simple theory of galaxy collisions to learn a lot about the galaxy and possibly about the formation of giant low surface brightness galaxies. So it shows the interplay between the science mission of HST and the amazing images and other data that come from it. And with that, I'm done.
Awesome. Thanks, Tony. Okay, so we have a handful of Astro-Images, and I think I'm just gonna go through them real quick. This is James Willingham. He had, there's actually a solar eclipse. We have to be out by 9, and I want to give people a little bit of time to play with some of the toys that we have here in the room. So I'm gonna go through these rather quickly. This is, it's not about, that's how James captured it. Arjun, are you on? Are you on, Arjun?
Yes, I'm on. Sorry about that.
Do you want to talk to this?
Yeah, so I just wanted to share a little bit about this. And so this was a video that I took from the window of my house. And I know this isn't like exactly astronomy related, and I know that astronomers don't really like clouds, but it looked really dramatic, and I think I wanted to share this from like an artistic point of view. It looks like something that would happen on like an exoplanet. And there are mostly stratus and cumulus clouds in this photo. And so I just wanted to share with you guys.
It's really dramatic.
Yeah.
It does look like you're in the middle of a wildfire or something.
Yeah, that's what I was thinking.
Okay, cool. Sorry, I wanted you to talk more about it, but I'm gonna just move on if that's all right.
Oh yeah, I understand.
Harini? I think this is a sea star image that Harini took.
Yes. So this is the image of the sun. I took it I think in the morning, and I was able to get some of the sunspots on the sun.
Yeah, I guess it hasn't been very good for nighttime astronomy, so you took advantage with some daytime astronomy. I see. Excellent. Yeah, those are there's some interesting little sunspots there. Thanks. Thank you for sharing. And Harini and Arjun both, I wanted to talk to you afterwards and see if you were interested in some of the experiment stuff that we talked about today, that our speaker spoke of. Gary is in the room.
Yeah, this is just obviously the Flame Nebula, a rare break in the clouds a week or so ago, and I just took advantage of it and got about, I think it was about 2 hours of total exposure time from my driveway in Columbia.
And this is with your smart scope.
With my Origin, yeah.
That's awesome.
This is right out of the scope. There's no special processing or anything.
It never ceases to amaze me how bright Alnitak is in any of these images.
Yeah, and the conditions were not great that night. I mean, I'm really looking forward to getting that scope out in some darker skies and under better seeing conditions to see what I can pull out of it.
And here's your other one.
Yeah, this one I took at the last public star party while I was looking at Jupiter with my SCT visually. I was running my Origin in the background, getting a shot of the Whirlpool galaxy. I was pretty pleased with. I mean, obviously the skies out there are a little bit darker, so I got a little bit better data.
Does this come right out of the Origin, or do you
right out of the
post-processing?
No post-processing.
Wow.
Now you can, because it keeps all the individual subs, and you can do post-processing and like picks inside or something.
That's amazing.
I'm too lazy.
What's the aperture?
6 inches.
And is that the full image or do you crop it?
This is cropped. That's the only touch up I did to it.
And Wayne, are you still on?
Yeah, so this is NGC 3718, or ARP 214. It's a 10th magnitude galaxy in Ursa Major. There's a Hickson group just to the lower left of it, of 5 galaxies, and then there's another NGC galaxy up to the upper left, NGC 3729.
Looks like this dovetails nicely with your collision presentation.
Yeah,
Some kind of collision's going on here. That's cool. It's an awesome.
yeah, they think it's a galaxy that's actually off the top of my frame, I think.
Huh. Cool. Thank you. And Gene, same object.
Look at that, the same one. Yeah, I saw Wayne's picture on that he had posted, and it's like, oh, I got to take a picture of this thing too. So, and
That's awesome.
yeah, I kind of think this is a sort of like the bullseye, except it didn't hit in the middle, but it was going perpendicular to the axis, the rotation, or parallel to the rotational axis.
Hmm. Awesome. And then you also had one more.
Yeah, so while I was waiting for that other galaxy to get high enough, I wanted to take a picture of something bright. So this is narrowband of the Crab Nebula.
Awesome. Awesome. I'm waiting for an amateur to do a time lapse of this over the years, just to watch it evolve.
Isn't there someone was?
There's been I don't know if there's amateurs in our. I don't think anybody in our club has done it, but there's definitely professional.
Yeah.
And then Phil.
Yeah, I was also looking for a bright object. I found one. It's actually bright enough to see during the daytime. So this is the hydrogen alpha. I obviously artificially colored it. People like looking at a yellow sun. So it was a very huge prominence coming off, and it was relatively faint on the outer part, but I was able to get that and the disc without any masking. So it came out pretty good.
Does that count as a CME? Is that a CME?
No, that's just a prominence that's hanging out there.
Okay.
So generally, if you have a coronal mass ejection, we've witnessed them live. I mean,
Yeah.
actually last time at Earth Day, it was one of the biggest
I remember
explosions we ever seen
Yes.
ever.
Right.
I mean, that we
At
witnessed, and it was
Clarksville,
gone
yeah.
in 20 minutes. But when you on the surface facing you, it gets to be very, very bright. And I've imaged some of them while they were doing it, and it was so bright that I couldn't even get Photoshop or anything to put a color on it.
Wow.
The white was so white, it was incredible. But yeah.
All right. Well, that
was
is
an off the edge shot.
amazing. I'm happy to see you sharing your solar photos. And that's it. So I want to say thank you to everybody who came. Thank you to our speakers. We have a few minutes, I think, to maybe play a little bit with some of the stuff that we have in the back. And we have some leaves and some dead leaves here, so we can look at them with this Stella instrument. So for those of you online, thank you so much, and hope to see you at a HAL event real soon.
Don't forget to stop recording.
Yeah, I'm looking for the menu. It always just it goes somewhere else. There it is.
I don't know why I was thinking of the other